I welcome you all in this lecture on modeling and simulation of dynamic systems. In this lecture we will see the basic system models, and under basic system models we will be looking at the modeling of electrical systems. As I have told you in my earlier lectures, now we are currently looking after the systems which are there in the different energy domains. So, in the last lecture we have seen the systems which are there in the mechanical energy domain. Today we will look at the systems which are there in the electrical energy domains, and then of course hydraulic, pneumatic and the thermal systems in these energy domains we are going to look at it. Now, as for the mechanical system, for electrical system also initially we will be seeing the three basic building blocks, okay, and the expressions corresponding to those three basic building blocks we will be looking at, and then we will use these basic building blocks to model a complicated electrical circuits or complicated electrical system. Okay. So, this is what this is how we plan to do it today. Now, the basic building block in electrical systems are inductors, capacitors and resistor. Okay. And these inductor, capacitor and resistor, using these three basic building blocks we can model any system. Okay. So, let us first of all look at the inductor. In this figure you can see the basic schematic of the inductor, and in an inductor actually the potential difference across it at any instant depends on the rate of change of current through it. In fact, this VL is basically proportional to di by dt, and when we replace this proportionality constant proportionality sign with a constant, this what we put L, we put the L for that. Okay. And here this L is what we call it as inductance. Okay. So, here you can see that if a current I passes through the inductor, and if rate of change of current we can represent here di by dt, then that into L is going to be giving us the voltage across it. Okay. Here the sign which you are seeing, that is basically for the back EMF, okay, that is the one which is in the reverse direction of the applied voltage. And from this expression we can find out the expression for the current which is going through it at any instant, and that is 1 by L integral of VL dt. So, this is how we can define the inductor or inductor characteristic. Next basic building block is the capacitor. Okay. You can see here the schematic of a capacitor. This is say the direction of current I, and this is again the direction for that back EMF V. Now, the capacitor can be defined as the element potential difference across it depends on the charge Q on the capacitor plate at the any instant. Okay. So, at the any instant whatever charge are there across the plate of that, based on that we can define the capacitance. Okay. So, you can see the Vc is basically Q by C. Okay. And here C is the what we call it as the capacitance of the capacitor, and I can replace Q here by integral of I dt, that is integration of current will give us the total charge accumulated across the capacitor plate. Okay. And from here I can find out what my current is going to be, that is C dVc by dt. Okay, that is, if I take the differentiation of it, I get the I is equal to C dVc by dt. Okay. So, this is how we define the capacitor. Next basic building block is resistor. Okay. And you can see this is the schematic of a resistor, and say current through resistor is I, and again here the direction of back EMF is shown. Okay. And the applied voltage direction will be reverse of that, and this the potential difference across it at any instant depends on the current through it. Okay. Of course, this relationship all of us know, very popular, the Ohm's law. Okay. So, the VR, that is the voltage across the resistor, is going to be I into R. Okay. And that is, it is going to be proportional to the current through it, and here R is the resistance of the resistor. Okay. So, these are the three basic building blocks which are used in writing the system equations for any electrical system. So, here I summarize the electrical system building blocks. This is a resistor. The basic equation VR, that is voltage drop across resistor, is I into R, where R is the resistance, I is the current. This is for the inductor. Okay. Here the voltage across inductor terminal is L di by dt, and from here I can write the expression for I as 1 by L integral VL dt, and this is the voltage across the capacitor plate which is Q by C, written again in terms of the current, and from here I can write the current expression. Okay. So, these are the three basic system building blocks. Now, let us see the energy and power associated with these elements. Okay. As we have seen, I have talked about these elements in our lecture on the bond graph modeling also. The inductor and capacitor, they are the energy, they are the energy storage elements, both store energy, whereas the resistor dissipates energy. Okay. So, energy stored by an inductor, as you can see here, when there is a current I through it, is given by half Li square. Okay. So, this I am not working on the derivation of it, you might have studied, it is just a review for you, that this is how we write the expression for the energy stored in an inductor when there is a current I through it. Similarly, if we talk about a capacitor, the energy stored by a capacitor when there is a potential difference V across its capacitor plates is E is equal to half CV square. Okay, where C is the capacitance of the capacitor. Okay. And as I said, a resistor will be dissipating power. Okay. And the power dissipated by resistor when there is a potential difference V across the two ends of it is given by VI, or I can write in terms of voltage and resistance as V square by R. Okay. So, this is how we define the energy stored in the inductor and capacitor and the power dissipated by the resistor. Now, if we want to build up a model of an electrical system, okay, we can do so by using the two laws of the Kirchhoff's. Okay. These laws of the Kirchhoff's are what we call it is the current law and the voltage law also people call it. Okay. And the first law basically tells about the current into a junction and current out from a junction. Okay. So, if we look at this simple electrical circuit where you have a applied voltage source say of V, there is a resistor of resistance R1 and there are two resistor again which are parallel to each other, say R2 and R3. Okay. Now, if you look at this junction A, you can see that there is a current coming into the junction which is I1 and the current going out from the junction are I2 and I3. Okay. So, this Kirchhoff's first law, it tells that the total current flowing towards a junction is equal to the total current flowing from that junction, okay, or the total current into a junction is equal to total current out from that junction, okay, or we can say it in other words as the algebraic sum of currents at a junction is equal to 0. Okay. So, this is the Kirchhoff's first law, okay, and I will be talking about Kirchhoff's second law also, and with the help of these two laws, okay, we can use them separately or we can use them in combination also, okay, we can derive the system equation for any electrical system. Okay. So, for this case you can see the current I1 is equal to I2 plus I3. So, current in at junction A is I1 and current out from junction A is I2 and I3. So, I1 is I2 plus I3. Okay. Now, here say if I take B as my reference voltage, okay, which is say ground, alright, then I can write this expression in terms of voltage. Okay. So, the voltage across R1 is V minus VA. Okay. So, I1 I can write V minus VA upon R1. Now, I get this expression from the resistance building block, okay, and I2 will be the voltage here, that is VA minus 0, that is VA divided by R2, and plus I3 will be VA minus 0 divided by R3. Okay. So, this way I can write the expression for this system, okay, and this is how we can implement the Kirchhoff's first law in order to get the system equation for this circuit. Okay. Fine. Next, let us see the law 2. Okay. Again I take the same circuit, the one which we have seen the previous one, that is I have got a voltage source, applied voltage here, then we have a resistor and there are say two other resistor R2 and R3. Now, this Kirchhoff's second law says that in a closed circuit or loop, the algebraic sum of the potential difference across each part of the circuit is equal to the applied EMF. Okay. Okay. That is, in a closed circuit or loop, the algebraic sum of the potential difference across each part of the circuit is equal to the applied EMF, or in other words, sum of the voltages around a closed loop or path is 0. Okay. So, this is what this principle says. Okay. So, here basically I can just explain how can we write the expression for this circuit which we have considered here. Say this is point A and here we have the two resistors and say this is my end B and this is my end A. So, say this resistance is R1, this is R2 and this is R3. Now, here what we do is that we assume a direction of current through the loop. Okay. So, suppose through this loop I assume a direction of current as I1 and say through this loop I assume a direction of current as I2. Okay. So, in this circuit you can see that we have got the two loops. First loop is constituted by voltage source resistor R1, resistor R2, and the second loop is constituted by resistor R2 and resistor R3. Okay. So, if I write expression for the first loop, it will be V is equal to say I1 R1, okay, because here we are considering I1 current to be flowing through all the elements here, okay. So, this is going to be the I1 R1 plus here basically you see that we are moving in this sense, and the current through this resistor, this I1, this is what we are taking as positive, and this current is I2. So, here basically this will be the direction for the I2 and this will be the direction for I1. So, we have to find out the net current, and so this is I1 minus I2 into R2. So, this is the expression, first expression, that is expression for the first loop. Okay. Similarly, I can write expression for the second loop. Now, in the second loop we do not have any source, alright. So, I can just write the source voltage as 0 and the current through this element is I2. So, it will be I2 R3, and here again you see that this sense we are taking to be positive. So, the net current in this direction will be what, I2 minus I1 into R2, okay. So, this is what I can write expression for the second loop, okay. So, this way we can write the equation for this system using the Kirchhoff's second law, okay, or which is also called as the voltage law. Now, next I will be explaining various examples, okay, where we will be taking the three building blocks, that is the inductor, resistor and capacitor, and we will be using either the Kirchhoff's current law or the Kirchhoff's voltage law, okay, in order to build the system equation for the given circuit, okay. So, let us take the first one, alright. So, this is a example of resistor capacitor system, okay. So, here we have a resistor and we have a capacitor, fine. Now, there is a voltage source V here. Let the current through the circuit is I, alright. So, what is input here? In this circuit the input is the voltage, okay, the source voltage, and say I am interested in finding out the voltage across the capacitor, okay. So, my output is my VC, voltage across capacitor. Now, I intend to find a relationship between the input voltage and the output voltage, okay. So, I want to find out relationship between input voltage V and the output voltage Vc, okay. So, by seeing the circuit as say a loop here, we can apply the Kirchhoff's voltage law, okay, or Kirchhoff's second law, fine. So, here the V, that is the source voltage, is equal to the voltage across resistor plus voltage across capacitor, okay. So, V is equal to VR plus Vc using the Kirchhoff's voltage law. Now, the VR, that is resistor voltage across resistor, we all of know from the Ohm's law that this is going to be I into R, okay, where I is the current through the resistor and R is the resistance, fine. Okay. Then for the capacitor I can write Vc is equal to Q by C, or this is 1 by C and Q I can write integral I dt, and from here I can write I as, if I take differentiation here, so I is equal to C dVc by dt, okay. So, my this expression VR I substitute IR, okay, and this Vc I already have, and now I replace for this replace for this I as C dVc by dt, and I get this expression. Now, you see this expression involves the input voltage V and the output voltage Vc, okay, which is of interest to us, and of course, the parameter of the circuits, that is C, capacitance of the capacitor and the resistor of the resistor, right. So, you can see that this equation is a first order differential equation. Okay. So, this is what is. Now, let us see another example. Now, this is example of resistor inductor system. Say we have a resistor and we have inductor, both are connected in series and there is a voltage source here, okay, which is again connected in series through both of these elements, and my interest is to find out the voltage across the inductor, that is the VL. Okay. So, again we can apply the Kirchhoff's voltage law, and here the V will be VR plus VL. Okay. VR we know that it is I into R, and for VL of course VL is the output here. So, what I actually need is I need to replace this I in terms of the VL. Okay. So, I go for the expression for the inductor, that is I use the expression for the inductor building block. Okay. So, this is VL is equal to L di by dt, and from here I get I is equal to 1 by L integral VL dt. Okay. And then I replace this I here and I get the expression involving the input voltage V and the output voltage VL. Okay. So, this way we can get the expression for this circuit, that is resistor inductor system. Next, let us see a resistor inductor capacitor system, okay, the RLC circuit. We have seen the same figure, same model in order to give you the first impression of the bond graph model. Okay. So, let us see how we deal with here, how we are able to develop the system equation using these three building blocks. Okay. So, again here we have a voltage source, a resistor, an inductor and a capacitor all in series, and say my interest is to find out the voltage across the capacitor. Okay. So, the input here is the voltage source and the output here is the voltage across the capacitor. Okay. So, this is there. So, we can again use the Kirchhoff's voltage law, and here this V is say VR plus VL plus VC, that is the voltage drop across the resistor, inductor and the capacitor, and this is going to be equal to the input voltage. Fine. Now, for resistor building block VR is equal to IR, okay, where I is the current through resistor and R is the resistance of resistor. Now, for inductor likewise I can write VL is L di by dt. Okay. So, if I do that, what I have is V is equal to IR for resistor plus L di by dt for inductor. I am not touching Vc because I want my expression in terms of Vc, because Vc is my output voltage. Okay. So, I want this expression in terms of Vc only. Now, the thing is that here you see I have got I's and I want to replace these I's in terms of Vc. Okay. So, I can write the expression for the current which is passing through the capacitor, okay, which is used to charge the capacitor as I is equal to C dVc by dt. Okay. And I can substitute this. So, V is equal to this Vc plus we have CR dVc by dt plus LC d square Vc by dt square. So, you can see here this equation is in terms of the input voltage V and the output voltage Vc, and moreover this equation is a second order differential equation. Okay. Fine. Let us see next another resistor inductor capacitor system, and in this example rather than using the Kirchhoff's voltage law, I would like to use the Kirchhoff's current law. Okay. So, let us see that my circuit is like this. Okay. We have a voltage source, a resistor, and here an inductor and capacitor, they are in parallel. Okay. Okay. And of course, both together are in series with resistor and the voltage source. Okay. So, here let us assume that there is a junction A and the current here through this junction is I1 is the in and I2 and I3 are the out, okay, at this junction A, and say B is my reference voltage, or which I can take as ground. Okay. Now, my interest is to find out the voltage across the capacitor, that is Vc. So, if I go by the nodal analysis, okay, and as I said, B is taken to be reference node and node A to be taken as potential Va relative to B, then I can write using Kirchhoff's current law that I1 is equal to I2 plus I3. Then I can replace for I1, I2 and I3 in terms of voltages. Okay. So, I1 will be here V minus Va by R, this I can get the total voltage difference across the two terminals here. So, V minus Va by R using the definition for the resistors building block. Likewise, I2 I can write here, I2 is the current which is used to charge this capacitor. So, I2 I can write as C dVA by dt, and I3 I can write here, that is current through inductor, as 1 by L integral Va dt. And once I substitute this here, okay, I substitute this I1, I2, I3 in this expression, this is what I get. So, this is the governing equation for this circuit. Let us see the analogy between the mechanical system which we have seen in previous submodule and the electrical system. Okay, there is always an analogy between the spring mass damper system and the RLC circuit. We have seen this analogy in our lecture on the bound graph also. Okay. So, you see that here I have got a spring mass damper system and here I have got a series RLC circuit, fine. So, if I want to write the expression for the resistance in an electrical circuit, this is I is equal to V by R, and if I want to write expression for damper in a mechanical system, then this is F is equal to C into V, where F is the force and C is the damping coefficient and V is the velocity. Now, if we compare these two expressions, you can see that the force is analogous to the current, okay, voltage is analogous to the velocity, and the damping coefficient is analogous to 1 by R. Okay. So, this way I can build an analogy between the electrical system and the mechanical system. So, the current in electrical system is analogous to the force in the mechanical system, and this analogy is also known as the current force analogy. Okay. And the potential difference in the electrical system is analogous to velocity in the mechanical system. 1 by R here in electrical system is analogous to damping constant in mechanical system, and similarly we can define that inductance is analogous to spring and the capacitance is analogous to mass in the mechanical system. Okay. So, this way we can define the analogy, and as I have seen in told you in my initial lectures, many times we use this analogy to model the big mechanical system, okay, because it is not always possible to see the variations or simulate a big mechanical system. So, what is done is that rather than that mechanical system, we can model an analogous electrical system and we can do the parametric variations there in the analogous electrical system, okay, and we can see the effect of the various components or various variations. I leave a exercise for you. If you can recall, this was a circuit which we have seen during bond graph modeling of electrical system, and I leave this exercise for you to derive the system equation for this system using the Kirchhoff's first and second law, okay, and yes, so you can work it out, and how we did in case of bond graph modeling was that we assumed sub models here, okay, and we created various sub models, and we drew the bond graph of the system, and then those sub models which were initially covered, they were gradually uncovered, and we could easily draw the bond graph model for that system. Okay. So, if you do this one, then you will appreciate the ease at which we could draw the bond graph model for the complicated electrical circuit like this. Okay. Thank you.